All right, well, I want to say good evening to everyone. Thank you for coming tonight. My name is Steve Turner. My FCC call sign is KJ6EIF. And the first thing I would like to do tonight is to acknowledge the participation of all these organizations that have helped us put this together. All of the presenters are members of MACS, McArcs, and WARS. And the focus of MACS is to support the county in emergency preparedness officially. McArcs is a less official, not really official, but a volunteer organization dedicated to practicing for emergency communications. And so we have a weekly practice net that everyone's welcome to join. Willits Amateur Radio Society is more of what you would call a club, a radio club. It has lots of social activities that also have a ham radio component to them so you can practice your skills. So I advise you all to explore those, and if you're interested, to participate. We'd also like to thank Adventist Health in Fort Bragg and Ukiah for the use of facilities. Acknowledge Public Health tonight for covering for one of the evenings that wasn't available at Adventist Health in Ukiah. And we also welcome Long Valley Health Center. Again, this is not the first time the health center has been one of our participation nodes, but we do appreciate you being there. So let's see if I can make the presentation work here. Okay, so we have scrambled up the topics a little bit from what you had expected. Tonight we're doing radio wave propagation, but this is a more logical order. I had thought I would not be here tonight, so we were kind of taking things in a little less logical order. So, how do those radio signals get where they're going? And what skills and theory do you need to know to optimize your signal so that you can talk to people you want to talk to when you want to talk to them? You heard last week, Mike talked about DC and AC current. And I'd like to repeat that because it's really crucial to radio. Direct current goes in one direction, from negative to positive, and AC current reverses frequently, back and forth, back and forth, back and forth. The reason that we use AC current in our house is it's easier to transport alternating current over great distances because we can transform it into a higher voltage, and the resistance in the wire that it's traveling on doesn't impede it as much as it would if it was the same voltage in DC. Direct current, because Edison really wanted direct current when he developed commercial electricity, but he was limited to a couple of blocks. And Westinghouse was able to demonstrate that alternating current was much more effective at serving large areas. And so we have alternating current in our houses, but we use direct current in our portable appliances like flashlights and so forth. If you look at alternating current over time, on an oscilloscope, for example, it starts to look like a wave as the voltage increases to the full positive potential, then declines, reverses direction to the full negative potential, and back to neutral again. That is one cycle of your alternating current. It's important that you remember cycles because everything comes from cycles. When DC flows through a conductor, it creates a stationary magnetic field around the wire. That doesn't do us much good. If you're near that, it can distort your compass, but that's about all it will do. However, when you have alternating current flowing through a conductor, the expansion and contraction and reversal of that magnetic field radiates out into space. And that is what creates the radio, the electromechanical waves that you're going to transmit from your radio. And that's why there are two components to the radio wave: the electric field and the magnetic field. Now, in this example, this conductive antenna that we have at the back, as the electrical field pulses between negative and positive and moves out into space, it carries a magnetic field with it that also is pulsing, but it is at a 90-degree angle. See if this angle is important. So the electrical field follows the electrical pulse, and the magnetic field is 90 degrees from that. Just an aside, I have composed these slides to have positive statements that correspond to the questions on your test for this section of the exam. So you need to know that the two components of the radio wave are the electric and magnetic field, and they are at right angles to one another. And you also need to know that the orientation of the electrical field, in this case horizontal, defines the radio wave's polarization. That's important. Okay. One of the test questions that you have would be, what can happen if the antennas at the opposite ends of a VHF or UHF line of sight radio link are not using the same polarization? The answer is that the signals could be significantly weaker, because that other antenna, if it's oriented the other way, will not pick up the magnetic portion of the electromagnetic field as well. Horizontal polarization is normally used for long distance CW and single sideband contacts on VHF and UHF bands. We haven't talked about emissions yet, but CW is Morse code emission, and single sideband is a vocal mode, a voice mode. And we're going to focus mostly on UHF and VHF for the first half of this presentation, which is where most of you will be operating in the beginning. Vertical polarization is used for local UHF and UHF and VHF FM contacts. FM is also a form of modulation, frequency modulation. The reason vertical polarization was chosen is because most of the vehicles that do mobile radio have a vertically polarized antenna on the roof of the car or on the trunk lid of the car. And because you can't get a good strong signal if you cross polarize, like these two antennas, this is a horizontal antenna, this is a vertical antenna, you will lose a significant amount of signal if you try to communicate between these two. You need to have the polarization the same. As it says here, if they're not using the same polarization, the signal strength is reduced. So the wavelength is the distance radio wave travels during one cycle of the electrical magnetic fields. So from here to here to here is one cycle. These cycles are counted every second, and that count is the frequency of the oscillation, the frequency of the electromagnetic radio wave. That wave is traveling at the speed of light, and you will have a couple of questions about that on the test. The speed of light is 300 million meters per second, approximately. That will be a test question. So as you increase the frequency of the oscillation, the wavelength gets shorter. You see, this slow oscillation has a long wavelength, but if you have a faster oscillation, the wavelength gets shorter, the wavelength between that distance that they're measuring. So there's an electromagnetic spectrum that goes from basically 1 cycle per second up to pretty much infinity. And light, visual light that we can see, is way up high on the electromagnetic spectrum. This graphic illustrates how the spectrum is divided into frequency bands. The bands have similar propagation characteristics and other similar characteristics, and that's why they were divided this way a long time ago. So the acronyms are very low frequency, medium frequencies. This is where the AM broadcast band is in medium frequencies, beginning at 3 megahertz, 3 million hertz, 3 million cycles per second, is the high frequency band, sometimes called shortwave. Multiply that times 10, you get to the 30 megahertz divide between high frequency and very high frequency. Very high frequency is where your VHF 2-meter band is, where VHF television used to be, where the FM radio frequencies that we still enjoy are. Multiply that by 10 again at 300 megahertz, and now you start into ultra high frequencies. The UHF TV band, cell phones are in the ultra high frequency range, which goes all the way to 3000 megahertz or 3 gigahertz. So we can refer to the electromagnetic waves either as their wavelength or their frequency. So you will need to memorize and remember that high frequency bands, these 3 bands, high frequency band is 3 to 30, multiplied by 10, VHF, very high frequency, is 30 to 300. And ultra high frequency is 300 to 3000 or 3 gigahertz. Each of those is a test question. And that if you want to find out the frequency, you divide the frequency into 300 to get the wavelength. And we'll talk a little bit more about that on the next slide. So this is a chart of all of the amateur radio bands that we have available to us. As technicians, you will have a portion of these. You will have Morse code privileges in 3 of the high frequency bands, and you will have phone privileges in the 10-meter band that we were talking about before the presentation started. This is the part of the band that Tim was talking about, this working DX, in other words, working foreign countries, just the other day. Right now, this band is hot as can be because the sunspot cycle is increasing and the sun is agitating the electromagnet or the ionosphere that surrounds the Earth. And we're going to talk about that in a couple slides. So your 2-meter band and the 1.25 meter bands, in other words, 144 megahertz or 2-meter band, and the 223 megahertz or 1.25 meter band are both VHF. The 450 megahertz band or 70 centimeter is UHF. And those are very common around here and very available. There's lots of repeaters that you can access on these 2 bands. So how does a signal propagate? How does it spread through the environment? It really depends on the frequency and the characteristics of the environment. And the environment not just being what we touch and feel around us, but also the upper atmosphere. The farther they go, the more these waves spread, and the waves are actually have particle characteristics and wave characteristics. So the particles of that electromagnetic energy get farther and farther apart, and thus the signal gets weaker and weaker as it goes farther and farther from the antenna or the source. With UHF and VHF, which is where most of you will start when you get your license, very high frequency and ultra high frequency, 2 meters and 70 centimeters bands, the energy basically travels in a straight line called direct path. Especially UHF, the signals are rarely heard beyond your radio horizon because UHF signals are not propagated or affected the same way as lower frequency signals are by the ionosphere. Fog and rain on the 2 and the 10 and 6 meter bands, in other words, 30 megahertz and 50 megahertz bands, don't have much effect on these bands. But the precipitation, like we're having today, will decrease the range of the UHF 450 megahertz band and up. In other words, the microwave bands, because the moisture in the air will actually impede the radio waves. And vegetation also affects those higher frequencies. These are test questions. There are a couple of qualities that do affect those frequencies: diffraction and refraction. Diffraction is really an edge effect, where the signal passes an edge and bends just a little bit because of going around that edge. And we used to see science experiments in school about that, how that would happen. As light went through a slit, it would bend. Refraction is how the speed of light changes as it goes from one medium like air into another medium like water. The light wave actually bends because of the speed change of it moving through that medium. So we can use that diffraction to our advantage, and we call it knife edge propagation or knife edge diffraction. It can actually bend your line of sight radio signal around an edge and around another edge maybe, so that you can get past some mountains. And that's really helpful around here when you can have that effect, and you can find that effect. I'm using an example of Ukiah to Fort Bragg here. Buildings, on the other hand, can block the line of sight, but they could also reflect the signal. Example here, reflecting a signal, or diffract the signal. You can get that knife edge propagation around a building edge. And also, if you have an omnidirectional antenna, which we'll talk about probably next week, in other words, an antenna that radiates in all directions at once, there might be a reflection coming off an airplane, a reflection coming off a building, and a direct line of sight signal all reaching your antenna at the same time. And that is called multipath propagation. And it can be distracting because it can create a disruption in the received signal. So if you have a directional antenna, you can often use the reflective capabilities of a building or a hill to get around a corner. I was able on 2 meters to talk from Ukiah to a repeater on Mount Vaca one time, and I'm sure that the signal was bouncing between the hills down through the Russian River Canyon before it got to that repeater. It was pretty cool. It's kind of a DX on VHF. So one of the things you also notice is that if you're mobiling with your VHF signal and listening to a fixed location like a repeater, you'll notice that the signal strength can go up and down significantly in a matter of feet, because you're getting all these different pathways bouncing off all these different things, and they'll create differing signal strengths. So sometimes you'll move your vehicle a couple of feet to get a better signal. Or if you're using a handheld radio, you'll move yourself and your radio a few feet to see if you can get a better signal to get through to whoever you're trying to reach. However, you can get increased error rates if you're using a digital mode of communication, because digital doesn't like to have confusing signals. It likes to have a very clear signal, but the multiple paths can actually confuse the decoding process. If you're mobiling and you're using a voice mode, it sounds like picket fencing. It sounds like a louder, softer, chopped up signal. These are also test questions. There is, however, some UHF and VHF atmospheric propagation. The visible horizon that you see is only a couple miles long. But because of refraction in the atmosphere, your signal can actually go a little bit around the curve of the Earth. Another opportunity we have in the lower atmosphere, in the atmosphere, the troposphere, where weather is formed, is that we can get a ducting, a refraction of the signal between different temperature air masses. And this is especially noticeable on VHF and UHF, these very high and ultra high frequencies. Their wavelengths are so short that they actually respond to this temperature gradient between the two levels of the atmosphere. It talks, in the test question, it talks about 300 miles, but I particularly know a couple people that have spoken to Hawaii from Fort Bragg when ducting was really prominent. And this all has to do with weather, and there are actually websites you can look at to see what the prediction is for ducting. So it's the temperature inversions that cause this refraction. Other kinds of propagation that you get in the lower to mid atmosphere on these higher bands, one of them is sporadic E. Now, if you look at this layer, the atmosphere is divided into layers by scientists who study it. The troposphere is where weather is created, then the stratosphere, then the D layer, which we're not going to talk about much today, but the D layer has a really nullifying effect on HF. Low frequency HF signals get absorbed in the D layer during the daytime. And so you can't talk very far at all on those bands in the daytime. In the evening, the D layer goes away because it's shining on it that energizes the D layer. So it goes away and the signals can get up higher into the atmosphere. The E layer right here is available to the higher bands, the 10-meter band, the 28 megahertz, which is the highest HF band, and 6 and 2 meters, 50 megahertz and 145 megahertz, VHF bands. They can be reflected off the E layer. It's called sporadic E, and that you can get over the horizon on that. The VHF signals, which would be 2 meters primarily, can also be reflected off aurora borealis waves, I guess you call them, which are just energized pathways in the upper atmosphere caused by radiation from the sun, and they will reflect the signal back. It's very distorted because it's a wavy inconsistent, erratic surface that the signals are reflecting off of. But there are a lot of people that really get off on finding sporadic E and aurora opportunities for propagation. Also, meteors leave an ionized trail of gas behind them as they shoot through the atmosphere. And with some bands like 6 meters and even occasionally on 2 meters, you can get reflected signals off of those, reflecting back or reflecting further on and down into to another station. It's a very poor quality signal, but a lot of people enjoy trying to send signals through this form of propagation. The best band is 6 meters. That's a test question. So now we're going to talk about the lower frequency bands, HF primarily, and again, a little bit of the VHF. The higher atmosphere, the region above the troposphere and the stratosphere, when you get up into the D and the E and the F layers, you can get around the world propagation on the HF bands. As it says here, the ionosphere gets charged electrically. Each of those levels of the atmosphere have a different reaction to that ionospheric charging. Like I said, the D layer actually absorbs some frequencies. The F layer reflects other frequencies. And there's an 11-year sunspot cycle. Right now, the sunspots are increasing. We're at the beginning of the 11-year, of the period of the 11-year cycle where the sunspots increase, and they'll get to a maximum, and then they'll start to decline and be at a minimum about 5 years from now, I guess, when it's at the nadir. Right now, the high frequencies and 6 meters are just hot as can be because the ionosphere is getting really charged by all the energy coming from those sunspots. And so signals are skipping all over the world. So one of your test questions will be, which of the following bands may provide long distance communications during the peak of the sunspot cycle? Like right now when there are so many sunspots. And the answer is 6 meters or 10 meters. 6 meters is 50 megahertz, 10 meters is 28 megahertz. And as a technician, you will have privileges on 10 meters. So it's a pretty cool time to get a license. But again, the capability of getting skipped is dependent upon the frequency, the angle of incidence. In other words, if your angle of radiation away from your antenna is too steep, it won't reflect back. It will go right out into space. If you have a lower escape angle on your antenna, it can be refracted back. We were talking before the class started about an antenna that I have that actually on 10 meters, it's not designed for 10 meters. So it has a very high angle of radiation on 10 meters. So it's not very good right now. So hopefully I'm going to add another antenna and make it a lower angle of radiation so I can get this reflection. If the frequencies are too high, like if I was trying to use 2 meters, 145 megahertz, it would go straight out into space unless it hit the meteor trail or the aurora, because the rest of the ionospheric layers would not reflect it back. So there's a test question. Ionic propagation is far more common on HF than VHF. UHF is usually not reflected by the ionosphere. Another thing to keep in mind is that when you get into ionospheric propagation, it no longer matters whether the antenna polarization matches the vertical polarization or the horizontal polarization, because the polarization gets all twisted up while it's reflecting off of all these moving energy clouds up in this ionosphere. So some of your test questions: 6 or 10 meter bands via the F region of the ionosphere during the peak of the sunspot cycle. 10 meters is best in the daytime during the high part of the sunspot cycle because of the F region. And skip is very rare on 144 and higher in the UHF bands. Skip referring to ionospheric propagation. And this was, I stated this earlier, because of all the different pathways through the ionosphere that randomly combine at the receiving antenna, there's irregular fading, and because of that, the vertical and horizontal polarization is not as critical, matching that up. Fading causes errors, data errors for digital signals, and again, polarization is as important in UHF.
What's in this section? In the safety section, the safety elements that are on this test include power circuits and hazardous voltages, electrical code compliance, circuit protection, lightning protection, a very big and important topic, antenna and tower safety, equally important for sure, tower grounding. What exposure hazards are there when you are around radio frequency energy? You need to understand those. But before we get into that, I want to take us back to last week, do a few review questions, so you can see how much you remembered from last week. So I will read the question, give you a second to think about it, and then I'll click on the right answer. So what type of electrical component consists of conductive surfaces separated by an insulator? Conductive surfaces separated by an insulator. And I'll give you a hint. It's able to store energy in an electric field. The answer to that is capacitor. So what's the name for the flow of electrons in an electric circuit? Now, when you have electrons moving in a circuit, there's a name for that. That phenomenon is known as resistance, voltage, capacitance. Nope. Current. Current's the name for the flow of electrons in an electric circuit. How about this one? What does the abbreviation FET stand for? Field effect transistor, fast electron transistor, free electron transmitter, or frequency emission transmitter. Well, they try to throw you off there. It's a transistor and it's a field effect transistor. Excuse me, that's in contrast to a bipolar junction transistor. Both of those devices have 3 contacts. On an FET, though, will be labeled drain, gate, and source. So those are the 3 contacts on a field effect transistor. So what's the electrical term for the force that causes electron flow? What makes that current flow in that circuit? What's the pressure? What's the force? It's voltage. So Mike last week talked about electronic components. One of them only allows current to flow in one direction. So what electronic component allows current to flow in only one direction? Driven element, fuse, resistor, or diode? No, it is a diode. Okay, Ohm's law was one of the things I talked about last week. So there's a formula that's used to calculate voltage in a circuit. If you know the resistance and the current, you can calculate voltage. Formula for that is B. Voltage, represented by E, equals the current in amps, I, times the resistance in ohms, R. So this was one of Mike's last questions last week too. What's a term to describe a device's ability to amplify a signal? Okay, transistors are devices that can amplify signals, and the property of that device that describes its ability to how well it amplifies a signal is the gain. So to describe a device's ability to amplify a signal, you refer to its gain. We talked about multipliers last week: milli, micro, mega, kilo, giga, all kinds of prefixes. So what is 1 microvolt? What is that equal to of those choices? 1/1,000,000th of a volt, 1,000,000 volts, 1,000 kilovolts, or 1,000th of a volt? Well, micro is millionth, so the correct answer is 1/1,000,000th of a volt is equal to 1 microvolt. Okay, enough review. We're going to get into the safety topics tonight, and this is really important because you have to be able to recognize the risks and hazards that might be present in the hobby in order to follow the appropriate safety rules to protect yourself and your family and neighbors for that much. So the human body can be fatally injured by contact with electrical circuits. It's the electrical current that does the damage to the body. How can electrical current damage the human body? Well, for one thing, it heats up the tissue that it travels through. It disrupts the electrical functions of the cells in that tissue, and it can cause involuntary muscle contractions. Those are all negative things that can be done by current that flows through your body. As little as 30 volts can be dangerous to a human, particularly if that current that flows as a result of that 30 volts goes through one arm, across the chest, and out the other arm. If you have your hands across a voltage source and that current flows through your chest, one of the things it can do, involuntary muscle contractions. You don't want that happening with the heart. So 30 volts or higher can be dangerous, particularly if it's flowing from one hand through the other, through the chest. Okay, if you remember Ohm's law, what does Ohm's law tell us? Well, it tells you that for a given resistance, if you increase the voltage, as the voltage increases for a given resistance, whatever the resistance is of your body, the current will increase. So higher voltages result in higher currents, therefore higher risks. So because of that, you need to take precautions if you're working around higher voltages. And that means if you're measuring a higher voltage, and this is in the hundreds of volts range, you need to make sure that the meter that you're using and the leads, the wires attached to it, are rated for that kind of voltage. Otherwise, you'll put yourself at risk. So batteries are a common thing, commonly used in amateur radio, usually in most mobile equipment. Your car has a battery in it. But one of the risks of the batteries is not so much the voltage. This is below that 30 volt threshold, but 12 volt storage batteries can deliver massive amounts of current. So what happens? Well, if you happen to short the terminals of a battery, 12 volt storage battery, say you drop a wrench across the terminals on your car battery and it shorts it out, you're in for some potentially terrible results. Shorted terminals can cause a fire, explosion, or burns because there's a tremendous amount of energy stored in that battery that's released all at once if it's been shorted. Batteries also present dangers if they are charged or discharged too quickly. The reason for that is there's a lot of heat that's released by that rapid discharge or that excessive charge. So you can overheat the battery. When you overheat that battery, it causes something that's known as outgassing. The chemical reaction inside that cell produces generally hydrogen gas. That's a flammable, explosive gas that's released during charging. So when you are charging batteries of that type, they need to be in a ventilated place so you don't allow that explosive gas to accumulate. So there's a lot of other basic rules for protecting your equipment and yourself with AC powered equipment, the stuff that you plug into the wall. First, you should use 3-wire power cords and outlets. This is pretty common. Back in the day, you'd only have two contacts on the plug, but most any house that's wired today, you'll have 3. And it's important to know what those 3 are. They're color-coded by the wire. If you peel back the insulation on an AC cord, not one that's plugged in, please, you'll see 3 wires. There's the black wire that represents the hot circuit in the AC line. There's a white wire that's the neutral circuit, and then a green wire, which is the equipment or the safety ground. And the other feature that you may use to protect yourself is to have mechanical interlocks on high voltage compartments. Not so much with the radios today, but if you have a high power amplifier that uses tubes to increase your signal, that may have several hundred volts inside parts of it. So safety says use an interlock so when you open that compartment, it de-energizes the circuit. So one thing you should do too, I mentioned the green wire is a safety ground. That wire should be attached to any exposed metal on your radio, and all of those safety grounds in your station should be connected. That prevents any unsafe voltage from appearing on any surface that you might be able to touch, conductive surface that you might be able to touch in your station. There is another risk that you should be aware of, and that is equipment such as a power supply that has filter capacitors in it. This comes from one of the questions. The charge stored in a filter capacitor, remember they store energy in an electric field, that can be unexpectedly discharged. It takes a while for that charge to bleed off. So if you've just turned something off, there is a risk, a hazard from a power supply immediately after turning it off because of the charge stored in the filter capacitors. Okay, last week, Mike showed you what the schematic of a symbol for a fuse looked like, explained what it's for. Get into that a little bit more. Fuses are important because they provide protection by removing power in case of overload. That's right out of the question pool. Fuses provide protection by removing power in case of overload. What does that mean? That means if there's excessive current, the fuse will fail or blow and it removes the power. It disconnects a circuit. When that happens and you go to replace that blown fuse, which has done its job, it sacrificed itself for your safety, you make sure that you replace it with the same capacity fuse. Fuses are rated in the maximum number of amps or amperes that they can conduct before they melt and give up and remove the power from the circuit. So you don't want to replace a 5 amp fuse with a 20 amp fuse, because then the 20 amp fuse would allow more current to flow before failing. And as a result of that, there could be overheating or a fire, because the fuse is oversized and it'll allow too much current to flow in the circuit. When you do install a fuse or a circuit breaker in AC powered equipment. A lot of hams, believe it or not, still build some of their equipment. And if you do that and it's AC powered, you want to make sure that that black wire, that black conductor, which is the hot conductor in the AC circuit, is where the fuse is installed. The fuse or circuit breaker are in series with that black or hot conductor. Okay, let's shift gears here and get up in the air. Let's talk about antennas. Amateur antennas bring another set of risks to you and your station. Care must be taken when installing antennas to avoid the danger of power lines. Potentially lethal combination, your antenna and a power line. So you need to, when you install an antenna, be aware of what might happen if it unexpectedly fell, and make sure that if it does, for some reason, a rope breaks, a guy wire breaks, whatever, and your antenna comes down, that there's at least 10 feet of clearance between where your antenna could fall and the power line. So you want to maintain minimum safe distance of 10 feet. Another thing, when you're installing antennas, or if you're building a tower components, look up. Make sure that there's no power lines above you. Really easy to miss. Always look up before you install an antenna. So another thing that you should not do, and I don't know if I had that on there, was do not mount your antenna to an active utility pole. That's a foolhardy thing to do. The utility company doesn't want you doing it, and the risk of that is your antenna could contact high voltage lines if you do so. So don't use a utility pole. I mean, you can get a used one and plant it in your yard with nothing else on it. Mount your antennas on that. That's fine. But don't go out and hook your antenna to one of PG&E's poles. Extremely risky and strongly frowned upon by the utilities. Okay, a lot of hams use towers to mount their antennas. You can get better performance. There's lots of good features of using a tower for an antenna support. And hams usually work in teams when they build or maintain antennas that are on towers, because one of the key elements is climber safety. I'm an old guy. I'm over 65 years old. I still climb towers occasionally, but there's a lot of risks that are associated with it. Physical risks, and you need to know some things before you climb a tower. First and foremost is it is not a job to be done alone. Never, ever, ever climb a tower without a helper or an observer present. To call 911 if necessary, if something happens to you. So never climb alone. If you are a climber, you need to make sure that you've had sufficient training, that you have an appropriate tie-off to the tower at all times. So when I'm climbing a tower, I always have part of the harness that I'm wearing tied to that tower, either with a belt that goes around the tower or a fall protection lanyard. But you need to have an appropriate tie-off and use an approved harness. Those are the three elements that they bring up in the question pool for a climber: sufficiently trained, appropriate tie-off, approved harness. This question is a little confusing potentially if you're not familiar with it. Some towers are fixed towers. You build them, you put one piece in the ground, you put another piece on top of that, another piece on top of that. Sometimes you use guy wires then to stabilize that tower. And if that's the case, anytime you have to do any work with the antennas or anything, you have to climb the tower. There are towers that retract, or they're called a crank-up tower. Different version of this, but in this case, they're referring to a telescoping type crank-up tower. And if you need to climb one of those, you need to make sure that that has been fully retracted, you've collapsed it all the way, or install mechanical safety locks in the tower if it's not fully retracted before you're climbing it, because you don't want to be on that tower and then have the telescoping sections slip into each other. A good way to lose your toes or your fingers or worse. So if you do climb a crank-up tower, make sure it's fully retracted. Again, look for overhead wires. Not all the risks are at ground level. They may be above your head. And as I mentioned, sometimes guy wires are used to stabilize the tower. Those apply tension to the tower. And in order to adjust that tension, typically you use a turnbuckle in the guy line to adjust the tension. That's awesome, that's great, but if you're using turnbuckles, you should use a safety wire after you've adjusted to the proper tension. You use a safety wire so the turnbuckle can't loosen on its own due to vibration. So the question refers to using safety wires on a guy line turnbuckle. Important feature. Okay, so what happens when you stick an antenna and or tower up in the air? My goodness, it becomes a target for lightning. And we're fortunate around here. We don't have as many lightning storms as you'll find in the Midwest, but you still have to be aware of the risks and what you can do to mitigate some of those risks. Because there's a serious risk of both personal and property damage due to lightning strike. And it doesn't have to be a direct lightning strike. There can be a nearby lightning strike that induces a voltage in your tower and or antenna and causes a voltage surge. So how do you protect up that? Well, you can put a device in the coax line. We'll get into that more next week about feed lines and coax. That's the cable that runs between your radio and the antenna. So you can put devices in the coax to protect equipment. And they're going to look something like this. Cable goes in one end, comes out the other. You'll notice there's a big screw on the side with a big fat tab on it. That's the grounding strap. So these would be mounted in the coax. They are mounted to a grounded panel, and that panel is usually located near the entrance to the structure. So you want to suppress any lightning surge before it enters the structure. So you'll mount those lightning surge protectors, as it says there on the device, to a grounded panel near the entrance to the structure. You will use grounding rods, again, to make sure that your station is safe. When you have multiple ground rods, you want to make sure they're all bonded or connected together. And when you do that with heavy gauge wire and or strap. So all your ground rods in your station should be interconnected or bonded with heavy wire or strap. Now, the requirements for grounding generally follow the National Electric Code, but they can be set by local authority. Your local building inspector is probably not going to come out and inspect your ham station. If you decide to erect a tower and put up a big antenna, you probably ought to check with the building authority and make sure that you follow all the rules. But the requirements for grounding ultimately are set by your local code. So, towers need to be grounded. Again, they're basically a huge lightning rod. And the proper way for grounding them, as dictated by most safety rules, is that for each leg of your tower, most towers have 3 legs, you'll drive a separate 8-foot ground rod in near the base of the tower, near each leg. So there's a separate 8-foot rod for each leg. Those are all bonded. or connected to each other and the tower. So the tower is connected to each of the three rods. The three rods are connected to each other. When you do those ground wire connections, the wire connection should be short and direct. You don't need a bunch of nice right angles or curly cues. Energy from lightning doesn't like to bend. It wants to travel in a straight line. So if you're grounding your tower for lightning protection, those ground wires connections should be short and direct. No sharp bends. Again, energy from lightning doesn't want to make a hard right or left turn. You want those connections short and direct. Okay, so let's go over some of the topics we just ran through. Which of the following is a safety hazard of a 12-volt storage battery? Touching both terminals with the hands can cause an electric shock. Well, no, not really, not at 12 volts. That's not a big hazard. Shorting the terminals can cause burns, fire, or an explosion. RF emissions from the battery. Well, batteries are DC, so I don't think there's any RF coming off of that. So D can't be correct because they're not all correct. Correct answer is shorting the terminals. You can release a tremendous amount of energy in a short period of time by shorting the terminals. That can cause burns, fire, or an explosion. What's the purpose of a fuse in an electrical circuit? Is it to prevent power supply ripple from damaging a circuit, to remove power in case of an overload, limit the current to prevent shocks, or all the choices are correct? No, the only reason you put a fuse or a circuit breaker in an electrical circuit is to make sure power is removed in case of overload, as it's worded in the question, in case of overload. That means in case it's drawing too much current. If there's excessive current, the fuse will fail and it will remove the power from the connection. So what's a good practice when installing ground wires on your tower for lightning protection? You put a drip loop in the ground connection so water doesn't damage the ground system. You make sure all those wires are nice, neat, right angle bends. Or do you ensure that all the connections are short and direct? Well, B and C are exclusive, so can't all be correct. The right thing to do is make sure all the connections are short and direct. Energy from lightning doesn't like to make rapid turns, wants to go in a straight line. Under what circumstances is it safe to climb a tower without a helper or observer? Well, hey, if you're not doing any electrical work, maybe it's okay, or maybe if there's no mechanical work, hey, you're only 20 feet off the ground. Nope. You don't climb a tower alone ever. It is never. And this is one of the times where you say never, you mean never. What's the minimum safe distance from a power line to allow when you're installing an antenna? Well, the important thing is you want to make sure if your antenna comes down unexpectedly, that no part of it can come closer than 10 feet to the power lines. Keep your antennas away from power lines, at least 10 feet. And realize if it comes down unexpectedly, you don't know where it's going to go. So give yourself plenty of clearance. Why would you avoid attaching an antenna to a utility pole? Well, antenna might not work properly, or the 60 hertz radiation from a feed line might increase your standing wave ratio. All these things are correct. Now, those first two are way out in left field. Biggest risk of attaching an antenna to a utility pole is you run the risk of contacting those high voltage power lines. Again, lethal combination. Okay. Final segment in safety is radio frequency exposure, RF exposure safety. And the FCC established these guidelines and added them to the question pool some years back. And basically they did this to protect not only hams, but their neighbors and families. First concept to understand that radio signals, here I say VHF or UHF, but any radio signal, HF, VH, UHF, all forms of RF energy are non-ionizing radiation. Well, what does that mean? What's non-ionizing radiation? Well, unlike radioactivity, which is ionizing radiation, radio frequency energy lacks the energy to change cells or damage DNA. That's right out of the question pool. So RF lacks the energy of ionizing radiation to change cells or damage the DNA. So RF is non-ionizing, doesn't have the oomph needed to damage cells, although it doesn't mean it's harmless. So let's talk about, excuse me, some of those risks from RF and what you need to know about them. Well, the FCC guidelines say that you as an operator, if you're a licensed operator, you're responsible for the compliance. It's up to you. Somebody's not going to come around and check it for you. You as the licensee are responsible for compliance. How can you determine whether your ham station is in compliance with the FCC guidelines? Well, there's three things that they tell you can do. You can do some calculations based on an FCC bulletin, OET Bulletin 65. There's information in there that tells you how to figure out what the exposure is. You can use a computer model. There are all kinds of programs available. You give it the input on the frequencies and distances and the antenna types, and it'll calculate the exposure level and tell you whether you're in the safety zone or not. Or you can actually measure what's called the field strength, the actual strength of the radio frequency field with calibrated equipment. Those are the three methods that are in the question as far as how you can determine whether your station is compliant. I will admit to you, I've had a ham radio license for over 30 years, and I have not applied any of these. So, however, my antennas are well away from where I operate the radio, so, and I don't run high power. Anyhow, those are the three things you need to know for the question. How can you determine if you're compliance? You use the FCC, the calculations in the FCC bulletin, you use a computer model, or you actually measure. You may need to make sure that you stay current. So if there's any changes in your station equipment, you put in a different radio, a bigger antenna, you now have an amplifier that allows you to run more power, you need to reevaluate. So if there's any changes in equipment, you need to reevaluate using one of those three methods shown above. So, again, the FCC guidelines say you as a licensee are the responsible party. One of the things you'll learn is the exposure limits. How much radio frequency energy can you safely be exposed to? Those limits vary with frequency. And there's a very good reason that they do that. You'll find that the most stringent exposure limits are in that VHF range, that 30 to 300 megahertz range. The reason for that is the human body absorbs radio frequency energy differently at different frequencies. And it turns out that at 50 megahertz, the 6 meter band, the human body is a pretty good absorber of energy. So what you'll find is the limits for exposure are lowest at 50 megahertz. So what are the factors that actually affect your RF exposure from a transmitting station? Well, frequency, as we just mentioned, because some frequencies are more readily absorbed by the human body, and the power level. So frequency and power level are one of the two factors that are two of the factors that affect your exposure. Another is your distance from the antenna. The further you are from that transmitting antenna, the less you're going to be exposed to the energy. As Steve mentioned, as those waves travel out, they diminish, they drop off. I think inverse of the square. So if you double the distance, you have a quarter of the exposure. So distance from the antenna and the antenna radiation pattern. Now, Steve's going to get into that a lot more next week. Different antennas send out their energy in different directions. Some almost equally in all directions. Some have very focused directions, and that's referred to as the antenna radiation pattern. So if the antenna creates a beam of energy and you're standing directly in that path of that beam, you're going to get a higher dose. So those are that are in the question, the factors affecting RF exposure, frequency, power level, distance from the antenna, and the antenna radiation pattern. Let me get a drink here. So another concept that comes into play in determining this permissible exposure level is the duty cycle. What is the duty cycle? That is the percentage of time that the transmitter is on during the averaging period. Sometimes your transmitter isn't operating all the time. Sometimes it's only on part of the time. That's the duty cycle. If it's only, say during a 4-minute period, the transmitter is only on 2 minutes, that's a 50% duty cycle. And it makes sense. The permitted power density increase is proportional to the duty cycle decrease. So if the duty cycle, the on period, gets shorter and shorter, the actual time that energy is present, the amount of energy that you're exposed to in that period can go up. And another thing is, and this seems pretty simple, but good practice is to keep your antenna out of reach, because if you touch an antenna while the transmitter is on, you run the risk of receiving an RF burn to your skin. Ever had it happen? I hear they're quite painful. Okay, so we're in a home stretch here. Let's run through some questions about RF safety. So why do exposure limits vary with frequency? Well, lower frequency RF fields have more energy. Nope, that's not true. Lower frequency RF fields do not penetrate the human body. Nope, that's not true. Higher frequencies are transient in nature. Well, no, they're either there or they're not. The answer is D, as we talked about. The human body absorbs more RF energy at some frequencies than others. And as I said, particularly in that 30 to 300 megahertz range is where the human body is a better sponge. What hazard is creating if you touch an antenna during a transmission? Electrocution, RF burn to the skin, radiation poisoning? No, it's the RF burn to the skin. You can actually get a burn from touching an antenna while the transmitter's on. So you keep your antenna out of reach. So which of the following frequencies does maximum permissible exposure have the lowest value? So of these frequencies that you have to choose from, which is the one where you can only, the exposure limit is the lowest, I guess? Is it 1296 megahertz, 3.5 megahertz, 440 megahertz, or 50 megahertz? Well, I mentioned earlier that the human body is particularly effective at 50 megahertz. So that's where you'll find the lowest permissible exposure level. What type of radiation signals are radio signals? Are they gamma, ionizing, alpha, or non-ionizing? Well, gamma, alpha, those are all forms of ionizing radiation. They pack enough punch that they can do cellular damage or modify DNA. Fortunately, radio signals do not fall in that category because they are non-ionizing radiation. So what factors affect the RF exposure of people near an amateur station antenna? Frequency and power level. Yeah, that makes sense. We know frequency will impact it. The distance you are from the antenna. Yep, the farther away from the antenna, the less exposure. and the radiation pattern of that antenna. If it points its energy in a certain direction and you're standing in that direction, you're going to get a higher dose. So all three of those factors, so all choices are correct.
Angle of incidence versus polarization. What's the difference there? I didn't quite catch that. You said that for skip, the polarization doesn't matter because it gets so...
it's mixed up.
Right. But the angle of incidence, I guess, if you have a, like, for example, if I have a dipole antenna for HF, a little slice that techs get access to, the polarization of that, if I understand correctly, would be omnidirectional. How do you, I guess I'm trying to understand the polarization of that in relation to the angle of incidence aspect.
Okay. You remember the moving wave coming off that, just that, it was basically a dipole. So if you look at my arm here, Brett, a dipole, yeah, there we go. Okay. A dipole is fed in the center and it's a half wavelength long. And because in this case, it's horizontally polarized. You can also have a vertical dipole if you want to string it up that way. But anyway, it's a horizontally polarized antenna. The angle of incidence on a horizontal dipole like this is basically all around it on the broad side. Now, the actual angle of incidence of the signal depends on how high you have that above the earth in relation to the wavelength of the signal. So at 2 meters, when the wavelength is 2 meters long, if you have this antenna, 2 meters is 7 feet, 8 feet. If you have it 7, 8 feet in the air, then the ground reflection doesn't matter as much anymore. It doesn't affect the signal. If you have a 10-meter antenna, which is 28 megahertz, and the wavelength is 10 meters, which is more like 30 feet. If you have this thing 7 feet off the ground, a lot of the energy is going to be going really high up because it'll be reflected off the earth. So your angle of incidence would be much higher than it would be for the 2-meter antenna. 2-meter antenna is not going to be reflected off the ionosphere, but the angle of incidence depends on the frequency and how high in wavelengths you have the antenna above the ground. That's the basic part. If you have a more complex antenna with more elements, and next week we'll talk about antennas, you can focus your signal in a narrower and narrower band of direction, and then your signal is really low to the horizon, so it has a low angle of incidence. So it goes, it hits the ionosphere at a lower angle, farther away, so your signal can actually go farther. If you hit the ionosphere at a higher angle and it is reflected, it's going to come down sooner. The bounce is going to be shorter. You want to have a low angle of incidence for those really long signal paths so that you go as far as you can before you bounce and hit the ground again. And I believe, Tim, please correct me if I'm wrong, but I believe typically in HF, a hop can only get about 600 miles per hop. So if you're trying to talk to Australia or South America, you're talking about it hopping more than once, bouncing more than once against the ionosphere and the ground or the ocean, which is ocean's better, before it gets that receiving antenna. I'm assuming that most people are here for emergency communication. Primarily, I really enjoy it as a hobby. I think Brett spends some time with it as a hobby too, and other people here. So mostly what you're going to be thinking about for emergency communication is making sure that you can communicate with the people you want to communicate with when it's important. So you'll need to think about the path of the signal that you're going to try and send. So for example, Mike, OTE, who's on the screen there, is in Fort Bragg. Um, he and I can talk directly on simplex, which is transmitting and receiving on the same frequency from my radio to his radio, only because I'm on a ridge top and I have a pretty clear shot toward Fort Bragg. If I was in the valley and Ukiah behind me, I probably couldn't get over the hill because I'd be too close to the hill. The angle of incidence of my signal to the top of that hill would be too sharp for that knife edge propagation to bring it back down into Fort Bragg. But where I am now, my only concern is that I'm shooting through foliage. My signal has to go through some trees. That impairs the signal. And it probably knife edges a little bit over some of the hills in between and creates some multipath. So we may have, and also that tropospheric ducting works locally too. When there's an inversion layer like we have today, we might have a lot better communication simplex between here and Fort Bragg than we would if we had a nice clear sky. It really does change from channel to channel and from hour to hour, and depending on the location too. So a lot of what you're going to be most interested in at first is how does your 2-meter radio work, because most people will start with a 2-meter radio. There are a lot of repeaters in this county that will take your signal and repeat it from a mountaintop. So if Mike and I can't talk directly on simplex, we go to one of the repeaters. The repeater's on a mountaintop. It receives my signal and rebroadcasts it on another adjacent channel down to Mike. And his radio does the same thing, sending his response back. And those repeaters, we have a plethora. We are blessed with so many repeaters in this county per capita that you wouldn't believe it. So there's a lot of opportunity to talk. There are at least 3 different repeaters that Mike and I could talk to each other through if we needed to. So, you know, if one of them isn't available, there's another one that could probably do just as well. So as you go through this, you need to be able to pass the test, but there are things that you'll probably focus on to begin with. And if you expand your interest into more of a hobby-like interest, then there's a whole range of things you can get into. You can get into electronics or physics or just computer applications, all kinds of things that can blend with your ham radio.
Is there a benefit to UHF as opposed to VHF? I mean, it just sounds like from your description, it sounded like there are some disadvantages in terms of precipitation, signal effects, and I can't remember what the other one was. But I guess I've never transmitted or tried to do that over UHF. So I'm wondering if there are any actual benefits. Why would somebody choose to transmit over UHF as opposed to VHF? Or is it just because there's more of the spectrum available to be able to do that?
Well, UHF goes through buildings better than VHF and the lower frequencies. Perhaps it's the tightly packed, the waves get closer together. Remember, the wavelengths get shorter and shorter as you increase the frequency. So perhaps it's the fact that they're tightly packed and concentrated. They can get through the molecular composition of the walls and so forth. That's why your routers in your house can get from one room to another, because that's a UHF signal, and it goes through the walls, and it's a little more permeating like that.
So it's better for a complicated environment, a local environment, but has less range in terms of distance.
Yes, and also if you're going in a digital mode, without getting too complicated, an antenna has an antenna needs to be resonant, and so in other words, it's tuned just like a tuning fork to a certain frequency. And it's not, as the further you get from that tuned frequency, the less effective that antenna is. And that distance, that effective width of the band pass of that antenna is considered percentage-wise. Let's say it's 5% of the frequency. So if your frequency is 4 megahertz, like the top of the 80 meter band or 75 meter band, 5% of that is only a few, maybe 100 kilohertz wide. At UHF, 5% of a 450 megahertz signal is 12 megahertz wide. So from a sliver of band pass that your antenna will pass to quite a big bandwidth of a signal. That's why, again, that our routers in our house use UHF frequencies, because in that 12 megahertz, now you've got, Nick could correct me, I'm sure I'm wrong, but you've got so much bandwidth, you can transmit a whole lot more information at one time. There's a function, or there's a direct relationship between how many bits of information you can transmit per second based on the bandwidth of your signal. And you can get more bandwidth at UHF and higher frequencies than you can at VHF and lower frequencies. And we do, one of the things that McCarks, well, McCarks doesn't sponsor it, but there is a net Tuesday nights, actually immediately following this, where people get on 2 meters and transmit digital signals back and forth, because you can send more information on a digital signal, even on 2 meters, in a given period of time than you can by speaking. One of my example, one time I sent the Gettysburg Address through this digital mode, and it took about 20 seconds to complete the entire digital transmission of the Gettysburg Address as text. Obviously, it wasn't voice, but it was text. So you can pack more information into that, and you can send information in the form of forms, reports or messages and so forth, on a format with digital modes. So if you're trying to do something like emergency response activity with a government agency, you can actually send them the forms that they want to see with the information that they want to see on it, with digital modes in 2 meters and UHF.
I do want to bring this up, Mike. Carol brought this up last time. There are a lot of resources available for working on the test questions. You can get the entire question pool, all 400 plus questions with the correct answers. There are plenty of online ones. The hamstudy.org. There are free apps available. There's other ones. They'll take you through the questions. They'll help you identify your strengths and the areas where you need to practice a little more. And although I have always used the yellow Gordon West guide, because I find it gives some pretty good explanations. The license manual, the 5th edition by ARRL, is a good one. And it, as Mike indicated, it gives you a little more in-depth explanations. It's a good resource, if nothing else. 2 of those things there I just mentioned say ARRL. What does that mean? That's the American Radio Relay League. Well, that's what it was originally called. Now it's just ARRL. It is over 100 years old. It is an amateur. It's an organization devoted entirely to amateur radio. It's an organization worth joining once you get a license. It helps support amateur radio in our country. The radio spectrum that hams have available to them is actually quite valuable. In many cases, the government can auction off sections of frequency spectrum and make all kinds of money. Our best protection to maintain our available spectrum is through organizations like ARRL that help support amateur radio causes, in Washington through lobby and other things. But we'll talk more about ARRL and other amateur organizations, but they're a tremendous resource. You can find study resources through them.
Yeah, I have one thing to add to your safety that actually isn't on the test. But if you happen to have a pacemaker and you're using a handheld radio, it has to be at least 8 inches away from the pacemaker. This puts out about 5 watts. If you're using a radio that's a mobile unit in a vehicle that's putting out 50 watts, you're normally safe because it's on the roof and you have a shield between you and the antenna. If you're using a high frequency radio, you have to be at least 10 feet away from that antenna when it's keyed, or it can affect the electrical circuitry in the pacemaker. I just wanted to point that out because I learned that personally. I happen to have a pacemaker, and I talked to the technician who was from the pacemaker company, and he looked it up, and those are distances that you have to maintain, or you can end up having a heart attack, basically.
I don't know if you guys have done the same thing as I have done, but before I got my ham radio license, I actually got a ham radio. About a Baofeng, which I'm sure you guys hopefully have heard of. It's a really inexpensive radio you can get for under $25 from Amazon. But if you go to the McCark's website and on the tab that says nets, it has all the nets that we have in the county, and it has the frequency. So if you have a radio, you can tune it to that frequency on those days, and you can actually listen in. You can't transmit, but you can listen in. So I thought I'd pass that on.